Welcome to this explainer. Today, we're diving into a genuinely fascinating historical mystery to discover how Mother Nature has actually already solved some of our most complex modern energy challenges. We often think of nuclear engineering and deep geological storage as these completely unprecedented human inventions. But as you're about to see, the Earth completely beat us to it, and by about 2 billion years. Okay, let's set the stage. Picture this. It's 1972, and a French nuclear processing plant at Tricastin notices a major discrepancy. Exactly 200 kilograms of weapons-grade uranium-235 is inexplicably missing from their Gabonese ore supply. They were doing routine mass spectrometry checks, and the numbers just were not adding up. And let me tell you, in the nuclear industry, missing uranium is the ultimate red flag. Because we are not just talking about a minor rounding error here. 200 kilograms, that's enough material for 6 nuclear bombs. Obviously, this immediately sparked massive fears of theft. Authorities were scrambling to figure out if this highly dangerous material had been diverted into unsanctioned weapons, or if something else entirely was going on beneath the Earth's surface. But well, as the scientists sent to investigate soon found out, nobody stole it. The uranium had actually been consumed right there in the ground. It was burned up by a naturally occurring nuclear reactor billions of years ago. What they uncovered at the Oklo mine in Gabon was a total game changer. It fundamentally shifted our understanding of geology, physics, and the entire planet's history. Section 1. The Missing Uranium Mystery. So, how did the puzzle pieces actually come together to prove that nature was our world's original nuclear engineer? Scientists didn't just guess. They looked at the hard, undeniable isotopic evidence. Normal U-235 concentration sits at exactly 0.720%. But the samples from Oklo, they measured 0.717, with some plunging way down to 0.296%. Combine that specific discrepancy with some really weird anomalies in fission products like neodymium and ruthenium, and scientists definitively proved a self-sustaining chain reaction had happened right there in the ore. Basically, the exact fingerprints of a nuclear reaction were permanently baked into the rock. Section 2. Nature's Nuclear Reactor. Now you might be wondering, how on earth, literally, does a nuclear reactor just exist without human intervention, or steel containment, or thick concrete? Well, look at this timeline. Thanks to the Great Oxidation Event 2 billion years ago, soluble uranium started gathering in highly concentrated groundwater veins. And here is the crazy part. Because U-235 decays faster than U-238, the natural concentration back then was around 3.1%. That happens to be the exact enrichment level we use in commercial reactors today. It's just a staggering coincidence. When that uranium gathered in high enough concentrations, it was perfectly enriched and ready for a chain reaction. No human centrifuges required. And get this, a chemist named Paul Kuroda actually predicted this exact phenomenon way back in 1956. He noted that a spontaneous reaction was simply inevitable as long as you met 3 specific conditions. You needed a deposit wide enough to trap neutrons, a U-235 concentration above 3% for fuel, and, crucially, groundwater to act as a neutron moderator. That water is the absolute key here. Without it acting as a moderator, the neutrons bounce around way too fast, and the chain reaction just fizzles out. This whole process brilliantly illustrates nature's built-in safety mechanisms. By looking at trapped xenon gas isotopes, scientists realized this natural reactor breathed like a living thing, cycling perfectly every 3 hours. Groundwater would seep in, slowing the neutrons and kicking off criticality. Then, as the reaction rapidly heated up the rock, it would literally boil the water away. No water meant no moderator, so the reaction instantly stopped. Then you'd have a nice, quiet 2.5-hour cooling period. Temperatures would drop, the groundwater would gently return, and the cycle would start all over again. It ran seamlessly like this for hundreds of thousands of years, completely naturally regulated, without a single catastrophic meltdown. Section 3. Copying Mother Nature's blueprint. So why does all this matter today? Because this historical curiosity is actually a mind-blowing blueprint for our modern environment. We don't just have to marvel at the Oklo reactor, we can use its exact lessons to solve today's biggest environmental crises. In geosciences, we call this looking at natural analogs, basically geological systems that have safely locked away hazardous substances for millions of years. These natural analogs are the ultimate proof of concept. They show us that deep geological storage isn't some untested, risky human experiment. It's a flawless, ancient, and totally natural phenomenon. To put things into perspective, we currently need to lock away CO2 for about 10,000 years to fight climate change. And highly radioactive waste? That needs to be secured for up to a staggering 1 million years. Both of these monumental tasks rely on the exact same geoscientific principles of fluid-rock interaction and multi-barrier containment that we see in nature. I know, those timeframes are literally impossible for the human mind to grasp, but for the Earth's geology, tens of thousands or even 1 million years is just a quick blink of an eye. Section 4. Locking away carbon dioxide. Let's look first at how we're currently mimicking this geology to trap carbon dioxide. This is obviously a critical piece of the climate change mitigation puzzle, and the blueprint is already mapped out right beneath our feet. Take a look at the Kitzen pilot site in Germany. Here, scientists successfully injected 67,000 metric tons of CO2 into a saline aquifer 650 meters underground. Using an incredibly intelligent network of monitoring boreholes, they tracked its spread perfectly. They essentially treated the Earth like a massive, porous sponge, tracking exactly how the gas migrated and proving, definitively, that this technology is ready for industrial application without the gas just leaking back up to the surface. Natural CO2 reservoirs have securely held gases for over 65 million years under places like the Colorado Plateau, and we're doing the exact same thing. It works in 4 progressive stages. First, structural trapping holds the gas under thick clay caprocks. Then, residual trapping immobilizes it in the rock's pores. Next, it dissolves into the saltwater. And finally, and this is the best part, mineral trapping takes over. The CO2 literally reacts with the rock to form permanent, stable crystal carbonates. So over time, the storage actually becomes safer and more secure as the gas turns into solid rock. Section 5. Securing radioactive waste. Okay, now let's pivot to the really tough one, securing high-level radioactive waste for 1 million years. Honestly, it sounds impossible for human engineering to guarantee anything for that long, unless, of course, we just copy what the Earth has already done. Look at this side-by-side comparison. On the left, we're engineering multiple barriers using corrosion-resistant containers and bentonite clay backfill. We do this to perfectly mimic the natural systems shown on the right, like the massive 50-meter-thick clay halo at Canada's Cigar Lake. That natural clay barrier has locked away highly concentrated uranium for 1.3 billion years. It's so effective that you can't even detect the radiation from the surface. And to guarantee these human-made repositories will hold up, we test them rigorously. At facilities like the Mont Terry Rock Lab in Switzerland, scientists are actively studying how radionuclides move through opalescent clay deep underground. They're gathering the precise real-world data needed to ensure that our modern engineered bentonite seals will behave exactly like those ancient, unyielding natural clay halos. And if we bring it all the way back to our Oklo reactor in Gabon, we see the absolute ultimate proof. Even without human-engineered casks or concrete bunkers, nature safely contained highly radioactive byproducts like plutonium right where they were created. And it did this with almost zero environmental impact. Think about that. Even completely exposed to flowing groundwater, the dangerous materials barely moved a few centimeters over the course of 2 billion years, entirely thanks to the natural trapping ability of the surrounding minerals. It's just incredible.
Section 6. A legacy for eternity.
So as we wrap up this explainer, consider what this massive geological history really means for us today. We have the scientific knowledge, and it is backed by billions of years of empirical planetary evidence. Now, the public often views carbon and nuclear storage with a lot of understandable skepticism. But the science shows us that Mother Nature has already run the ultimate beta test. She's executed these exact same containment experiments flawlessly for eons. Deep geological storage doesn't just manage a human-made risk, it transforms it into a proven, naturally occurring phenomenon. We aren't just crossing our fingers and hoping a new tech works. We're copying a system that has already survived the ultimate test of time. Knowing that the Earth itself has handed us this perfect geological blueprint, doesn't it demand that we confidently embrace these natural analogs? We have the tools to protect our planet for the next 1 million years. I really hope this explainer has shifted how you view the ground beneath our feet and the incredibly elegant, ancient solutions it offers for our future. Thanks for watching.